Hello all. Glad to be here. Thank you for HPC QP for organizing this and inviting Kilimanjaro. So I'm Albert Solana, the Chief Business Officer in Kilimanjaro. And today we're going to present the Qibo. Actually, Ellie has already presented part of that, so it is not. I'm not presenting this as new. So at least you got some reference. But here, what we want to present is like our work from a hardware perspective of a quantum computer provider, how we can interact with the HPC centers. So we've already been engaged in some conversation of that, and there's I would say a lot of work going on, and this kind of one of our approach and. Let's see. I guess you like about that. So yeah, the work that we have. Yeah, I have the same issues. Okay. Yeah. So let me first introduce Kilimanjaro. So we are quantum experts, right? Quantum specialists. Kilimanjaro is a company based here in Barcelona. We are actually 4 years. Just last week. Had and tomorrow we're gonna do the 4th anniversary party. Right now we are kind of 30 people, full-time employees here in Barcelona. A lot of PhDs, a lot of physicists. Myself, I'm the only one, or the few that are not physicists. I'm from my computer engineering background. But we are growing because quantum computer is a super huge industry that is growing fast. So here we are, and a lot of we are international people because as you can imagine, it's not only for Europe, it's also like global scale. So we need to grow and grow fast and collaborate. That is something that we want to mention, that it's not like one company is gonna solve that issues. The whole ecosystem is needed. No, there's another one here. Says I can try to do both, but not. If you can switch to the next one. Okay, yeah. So basically, I said we are quantum hardware providers, but what we are doing. So basically, our main product, our solution is called quantum ASICs. So basically what we want to bring is the quantum benefits now, which means that instead of going to the universal solution, what we are focusing into an application-specific solutions. So basically we are building chips that focus in one specific use case or a family of use cases that are requested for our clients. And this is what we call quantum ASICs. Actually, we got this year a grant for an European Innovation Council, basically to build the first prototype of these solutions. We're partnering with 1Qubit, which is a quantum software company from Canada, and CQIR, which is a research institution from India. So basically, this first prototype is going to be focused on chemistry, and we want to mimic the chemical reactions of a super basic molecule, like hydrogen and different combinations. So something that can be totally emulated in a laptop, but we want to show the proof that, okay, you can do this into a quantum. And actually, because nature is quantum, is analog, right? So what we want to mimic is the nature, how a molecule can react and actually mimic that the whole evolution into one of the quantum chips. Our chips are based in superconducting and technology. And let me go to the next one. Okay. So I already moved. Well, you train, and so I said we are based in superconducting, but our focus is also most of the players in the quantum industry are focused on the digital quantum computer. Some of other players, and Kilimanjaro is one of them, we are focused on analog, and so there's different types of architectures, but basically we are separating the quantum focus into quantum computer focus into two realms. Basically, when you encode, and most of you are more familiar with the digital model, because then you think about logic, and quantum logic is quantum gate. So basically, when in analog, when you encode a program, you encode as a Hamiltonian, this is your problem, and you go from a super basic Hamiltonian into Hamiltonian that encodes the solution of your problem. And we let the system evolve, and this is called, we need to get the schedule of going from one Hamiltonian to another one. I mean, not going to the specific details, but basically here what I want to say is that because this is continuous and we are not sending a specific gates, meaning a specific pulses, we do not rely that much on solving error correction. And this is a super helpful advantage. This is why we say that we want to bring the quantum benefits now, because at least for the small version of the chips, we may want to achieve also universal, but it's like a super long term. What we want to deliver first is like a small chips that then they don't need that much that error correction, so we can already show proof of that technology. So this is why we are focusing on analog. This is not going either. Okay, so and I think that just to finalize about Kilimanjaro, so basically we are providing already value to the clients. We have opened at the very beginning the consultancy on algorithms, so basically helping clients on how they can adapt their algorithms, their solutions into quantum, either again, where we go quantum ready, or to prepare either with the solution using emulator as well, as Eli was mentioning, right? This is a go-to right now. You at least you can start educating the clients and the community how to adapt your algorithms, your solutions into the quantum solutions. And so this is one part of the equation, let's say, and then the other part is about hardware, because so we are already deploying quantum computers. We did the first installations in the United Arab Emirates, but this was a transmon, so superconducting, but digital gate-based system, because we wanted to show that, okay, we have the expertise on doing that, and because our chips are based on the same technology, then it helps also to build our team. So we are building the quantum ASICs, and actually just this year we also had these big announcements that we, Kilimanjaro with GMB got we were the winners of installing the first supercomputing here in Spain in the Barcelona Supercomputing Center, and today we're gonna go to the Barcelona Supercomputing Center. You won't see the preparation, the installation. Actually, the first part is gonna provide access to our quantum computer, an initial chip, but within our installations, and we are going to start building, let's say, the quantum computer by the end of this year in their facilities. So because there's gonna some work being done on that for adapting the new Mare Nostrum, right? But we are super happy on that, and this actually get some tractions into also understanding to the community what is a quantum computer here in Spain, also in Europe to have another one, and this is important. And now getting close to the talk is like, because then it helps us as a quantum computer provider, how we can interact with the HPC center. What are really their needs in terms of computation? How these two types of architectures can communicate together. So basically, and this is one of the main points that I wanted to bring here, is like, okay, how they can communicate together. What is a quantum computer? How they can interact with that? Is really a dream or a reality? Because when I'm talking with the people working in the HPC centers, they see, well, first, they don't believe that much in the quantum computer, and I understand, because it's still an experimental process. So there's, right now it's kind of a toy model for them. But we still need to understand what are the benefits, so we are ready to start interacting with that. For that, Kilimanjaro was also invited last year in one of the workshops organized by EU. It was the European Quantum System Software Summit. So basically, there was several HPC centers, and they invited some quantum computer providers and also quantum solutions providers. So basically the idea, okay, how we can interact together. And this is one of the workflows that was kind of the initial of the workshop, right? So you can see basically the typical, I would say, workflow that is currently happening in the HPC centers. I'm not one of them, so I might be wrong. But basically, it's like, the idea is like from one model, one application, it gets into a static compiler, then it gets into the schedule, but this schedule is organized by an HPC model, let's say, where there's some tasks that need to be done. They are distributed throughout all the schedule, all the resources that the HPC center has, and then they see QPU, right, as an accelerator. So, okay, I see if I have 100 tasks, then, okay, these two may have logic to be sent into a QPU. So then it goes to the QC quantum computer schedule, and then it gets executed. I guess you see my pointer, yeah. So basically, they see that. One of the main issues that I raised there is like the vision, and here the thing that I want to bring to you is the vision, what I see in terms of the quantum computer. What happens for running an algorithm in a quantum computer where actually it requires also like some classical resources. So for that, let me first introduce our full stack, and then I'm gonna go back to that model and understand what is our vision. So here's our stack that we have developed, right? I said that we provide a quantum computer, but also we are full stack, so people can actually send an algorithm as IBM is doing right now, as other providers, right? So people can send their jobs and to be executed remotely. If you see this full stack, I usually when I explain this, I separate into 3 different layers. So first, the top one, which is Qibo, and this Qibo is the open source. Eli already introduced that, and we are one of the contributors of this Qibo framework. So people can code an algorithm using Qibo. Qibo is based on Python as well, similarly as Circ or Qiskit, pretty similar. And then again, this is open source, and we are using this, but then it enters into the quantum as a service, because then it goes into the backend. So the quantum as a service, you should think about, and we created this library, you can download Qibo connection. So basically is, you can run your algorithm in your laptop using Qibo connection. It gets into the backend, and you have your algorithm in your laptop, in your environment, and you don't need to connect, let's say, to our premises. And this is something that I noticed different from when you connect to an HPC center, that you need to connect directly to the system. So then it's like, okay, I see a terminal, and here, at least from different quantum providers, because we need to connect to B2B, right, to other companies, so we cannot provide direct access into a terminal. So our clients, let's say, they want super user-friendly. If I show them a terminal, they don't want to interact with that, right? Because the barrier is much larger. So the idea here, we provided that, and then from this Qibo connection, it goes to the cloud. It goes. We have deployed a system in the cloud. So basically, it's as an API that you can schedule your jobs, queue your jobs, and then it gets, depending on the device, you can select and you have access to. Then it goes to the specific lab that we have different devices. And for doing that, actually, and this layer, we want to be as agnostic as possible. So the idea is like from Qibo, basically, it gets converted or serialized into a OpenCASM, and there's already been some conversations, some talks today that already mentioned that. So basically, we want to be, and actually we are in collaboration with institutions, and IBM is one of them, working on OpenCASM version 3. So actually, what we want is use Qibo, but we don't require for the users to use Qibo. So it can be any other computing frameworks that allows them to serialize into OpenCASM. So the OpenCASM is the entry point, and then it gets into the specific lab. And then again, it can be a quantum backend, and I'm gonna get into more details into that, but it can also be an emulator, and there's also a library, QPUs, that uses also multiple GPUs that can run, again, because right now, and I'm gonna get into that in a minute, the QPUs are not ready yet for being into kind of a production mode. So then, okay, let's educate people, because there's a long process. It's not as easy as, okay, disconnect from here and I connect to there. All the algorithms need to be adapted for doing that. So in that sense, Qibo is also super useful for doing that, because actually you are educating the clients on how to use all the stack, and then it goes to an emulator, and because they are expensive, and multiple GPUs, so then it gets connected. And the same process we are doing, actually we are partnering with NVIDIA as well for connecting to their new DGX machines, and here we also have the possibilities to connect to an HPC node, so using the same stack. So getting into a little more detail into the quantum, because there's also a Qibo lab with the same stack from Qibo that is open source, but in Kilimanjaro, we built our own version of Qibo lab, which is qililab, basically because we are building a different type of technology. As I was saying, we are doing analog, and this type of chips is superconducting, and the type of qubits are flux qubits. I did not mention that. So basically, let's go a little more deeper into that, because that's going to help you understand why I'm saying that we have a different vision for how to scale the jobs. So a quantum backend has many layers, and so again, going to the top application language, but then it's like you see a black box, a magic black box which says QPU, right? But actually, before going to the QPU, where there's actually the chip into this cryogenic fridge, and everything goes down, and that we send the microwave pulses. But before that, there's a lot of electronics going on, and actually there's a computer connected to those devices. So there's many layers here where the language, either a quantum circuit, can be compiled. There's logical levels that gets into the knowledge of what is your QPU, and gets compiled, and then it gets to for instance here, we use as an example Qblocks, which is a control device that we use in the lab, and gets into the device control and gets to the QPU. So these many layers, actually, they require classical computing, which seems a paradox, right? You want to run something quantum, then it needs classical resources. Like, why? So okay, let me explain you a little from a use case that we do on our system. So basically, I said that we were encoding instead of quantum circuits a Hamiltonian, but I'm gonna do the same analogy for both applications. So from a user application, it needs an efficient encoded Hamiltonian, because if you encode something, your problem, let's say badly, then all the possible efficiency that you may have in the QPU or using quantum, it gets lost directly in this encoding problem. So we need a system that understands what is the best encoding process possible, and it takes time, and takes computing time. Second, when we need to pass through this Hamiltonian into the specific, let's say, again, maybe if you are more familiar to quantum gates, what is the minimum version of your quantum circuit, right? So you need kind of optimization process on that. Similarly, in the Hamiltonian or annealing, we need to find the best annealing schedule that actually corresponds with all the fluxes, taking into account the chip topology. So basically, at that level, you need to get the information to the QPU, get to here, and then perform another optimization. Again, these optimizations need to be classical. Right now, because we are dealing with super small chips, it can be done in the same server that we have in the lab, but we may need classical resources in the future, in the near future, actually. And then, okay, from this, you have a schedule, and what you need here is, and specifically, I told that in the digital, you have the error correction, and here you may consider how you can start mitigating the error correction for the gates that you are sending, how you can optimize all the pulses that needs to be sent. In the analog world, what we need is the crosstalk. So basically, when you send a microwave to a specific line, to one specific qubit, what happens nearby may be affected as well. So basically, you need to take into account all that. So this is a matrix of crosstalk. Again, if you are dealing with few qubits, that's no problem. But when you are going to larger scale, this is a major problem. So we need here an optimization, AI models in order to figure out this crosstalk. And again, this can be dynamic, But then for all the executions, all the runs, you can start like a learning process. So then you can be quickly going to what is the best matrix for the crosstalk sending to this circuit. So this is something that we can iterate a lot. And then it gets into the assembler schedule. And I use here a schedule because here is one of the, actually what I saw for the first time, it was kind of a surprise. And let me explain you a little about that. So basically here, there's the device control and it has an FPGA, where basically you send your circuit basically into that FPGA, into that memory, that this is what it needs to run. So basically here, there's also like the possibility that you can schedule several types of your problems into that specific memory. And again, think about the user, it goes here, and you can define different types of the same problem here in the FPGA. So this is something to be taken into account. And then finally, when you run your circuit, you have also a post-processing result that you can take. All to say basically is like when you send something remotely, right now what we are focusing on, what is the interaction between HPC and QPUs. Basically, we see that here at least we need this collaboration. The user may not know nothing about that. They are using also like classical resources, but this is something that at least the quantum computing industry will need. And this is something that we were providing as an exercise, again, as I said in this European workshop that we were participating, where actually we're saying, okay, there's the quantum computer users, low level, high level, and end user, that we have this stack that I presented to you. But then, okay, there's also the HPC users, right? And HPC developers, that also there's a high level or end user that wants to run something in the HPC center right now. They have their own libraries and they have their own developers knowing about the architecture. Okay, so here the idea and the challenge is how we can approximate all together to think about solutions that goes into this HPC QC kind of solutions. It's like the end user shouldn't care about what is the architecture that goes on below that, and then there should be new software developers knowing about how are the libraries and how are their quantum software developers. And again, in terms of architecture, we should need kind of also developers kind of more aware of the technology, and then so we can bring all this stack together, and then for sure, then we can communicate and we can see the workflow, initial workflow that I present to you, it can be really a reality. And with that, thank you very much.
Thank you so much. We have plenty of room for questions.
You can ask, I mean.
I have plenty of questions, always. Well, you show that the pipeline is the compiling. You are transpiling also at the same time of compiling. How much effort in development and in resources the pipeline is taking to this pipeline on the compiler? We have more or less the same compiler with transpiler. Then we have the IoT to parallelize on the logical level. We are trying to send, we were talking about the output problem we have for the outcomes. So we are trying to parallelize. The difference I see is between compiler and we put the layer of transpiler, and it takes a lot of resources from our side. I don't know if this is a difference for the general gates or you are going analog. Are you doing also transpiling of the circuit, and how much resources it takes to do?
Yeah, and actually, because I said that we are also doing gate-based, and all the stack are basically the same. And actually, we are also thinking and doing kind of an algorithm which is hybrid, because we have kind of the luxury that the technology that we are building for the analog is also superconducting. So when you are dealing with flux qubit, actually, if you set a flux into a specific tone, basically it is a transmon qubit, basically. but a fancy one, let's say, right? So basically, we are also building the same. So actually, our first test, because we have more documentation on the gate base, so we are doing actually the same in terms of transpiler. So actually, we are dealing with pulses, we are dealing with all the stack, and then we say, okay, and then we calibrate the qubits into the gate base, and then we move into the analog, because there's no exactly calibration process in that regard. But right now, we are already building these blocks. We are not in the phase of okay, how we can optimize that, because what we are focusing on is into the quality of the chips that we have. They are super small. And then the resources needed, as I said before, is we can even use it into a specific server. Right now is that we are in engaging conversation with, for instance, NVIDIA, in order how we can be super close to the QPUs and all these stacks, so then we can use those resources. Yeah.
This is what we call what's the runtime.
Exactly. Yeah. Exactly. So the user doesn't know. So we want to run a specific algorithm, and then we pick that and we block all the resources for that execution. Yeah.
To reduce a lot the delay between the execution. Yeah.
Totally. So yeah, and this is important, because the delay. So that's why we want to use that type of level, because here is pretty close connected to here. So we are talking also in nanoseconds, because we are sending into gigahertz, right? While from going to this level to this one, because then it goes to a server, you are having microseconds delay. So everything that also can be super optimized and gets into the FPGA, that's super, that's efficient. But I mean, that's what I'm thinking about, how an HPC schedule can be saying, okay, this is a job to be sent into a QPU. There's so many layers that need to be still encoded and super difficult to automatize. There's a long ongoing research for that, but it's still, it's good at least to think about that and where are the bottlenecks, because solving maybe one that is not a bottleneck, but it's a cool feature, but it's like, okay, where are the bottlenecks? I think it's important.
Yeah, absolutely. In fact, well, the runtime what solved is previously you send from the Qibo layer, you send to the QPU, and then you have to wait. You compile everything, but you send just the waves. Another question I have is, this is curiosity. We're trying to be backend agnostics, as you are also with Qibo.
Yeah.
Are you developing some kind of agnosticy on the backend using either analog or general one?
I mean, we try to, I would say, but so even we try to be agnostic as into this level, right? So it depends on, like, okay, this is the let's say open chasm, right? That goes here, and then and actually Qibo Lab is open source because of that. They want to be as agnostic as possible, but what we see is that, okay, let's build our own, and then let's see, and even we want to, be as general as possible. But always it gets into the specific instance. So I would say that the need to do an effort on saying, okay, this is how we encode right now, and then let's build like the same stack, but here as a backend, and then let's propose kind of a standard, right? Open chasm maybe for the language, and then another open chasm for the backend, so something like that. But yeah, I would say that is still ongoing. I mean,
yeah, well, at least it relieves to me that we are all of us are working on MVP mode. So
exactly. Yeah. Everything can be changed, and yeah, we should be able to change fast. Yeah. Yeah. Thank you.
Any more questions?
Well, I have one. It's related about dissemination of the Qibo platform. If you in Kilimanjaro are thinking about doing some open to the community, like hackathons, something related to that, how to use the platform.
Yeah, good point. I mean, we were only 30 people, and we are doing all that. So, I mean, we have many, let's say, topics that we want to embark. And actually, I think 2 weeks ago, a couple of our team went to ATH Zurich to do a hackathon actually, and present like, okay, this is the challenge, and the challenge needs to be done in Qibo. And it was a great opportunity to also showcase that Qibo also is, it's a language that you can encode your algorithms. And yeah, that is something super useful, and also to be engaged in here in, for instance, in Barcelona, that has several universities on that and masters. So be engaged with them, kind of educating also on how to engage into the quantum realm. That's super useful, and they're super excited. I mean, two days. I mean, they're super young, but 2 days without sleeping, and they work a lot. I mean, it's fantastic. Yeah, hackathon. I mean, IBM is doing many of those. So yeah.
It was not 2 weeks, but maybe 3 or 4 weeks.
Yeah.
We had the one in the hackathon in Barcelona, also the evening in IFO, and Kilimanjaro were there. Maybe next year we can talk about Qibo.
Totally. Yeah.
Awesome. Thank you so much.
Okay. Thank you.